Welcome back to my YouTube channel. The goal of today's video is to help you prepare for your forthcoming exam 2. I'll be covering how to solve box problems, mechanisms, and synthesis. And now let's get started. To provide the answer to this box problem, we need to recognize that this is a reaction involving two steps. So in the first part of the reaction, we'll be treating the ketone with the amine. So whenever we react a ketone with an amine, the product is usually an imine. And to draw the product, simply start by drawing your ketone, then replace the oxygen of the ketone with the nitrogen of the amine. The alkyl group on the amine, on the nitrogen, will remain the same. So usually water is lost in this reaction. So the oxygen from the ketone and the hydrogen from the amine will be eliminated in the form of water. So this is going to be the product from the first step of this reaction. Now when you treat imine with sodium borohydride, the sodium borohydride will reduce the imine to an amine. And that's going to be the product of this reaction. In this question, we're asked to figure out what reactant will react with thionyl chloride, followed by a reaction with this Gilman reagent in order to give us this product. So when you treat acid chloride with a Gilman reagent, only one of the alkyl group will replace the Cl group. And so your product in this case will be, so simply replace the Cl from the acid chloride with the alkyl group, with the Al group from the Gilman reagent. Cyclohexane is attached to this carbonyl carbon in the product. So that means our acid chloride will have this component in it. So what reagents can we react? Do we normally react with thionyl chloride to give us acid chloride? And that's carboxylic acid. So thionyl chloride converts carboxylic acid to acid chloride. So what kind of carboxylic acid are we going to have in the box? So that carboxylic acid should be based on this particular acid chloride. So all I'm going to do is to replace the Cl group with OH. So we're asked to provide the product for this reaction. So when you treat amide with the first reagent, when you hydrolyze amide, the amide is converted to carboxylic acid. Now when you treat carboxylic acid with thionyl chloride in step 2, that carboxylic acid is converted to acid chloride. And when you treat acid chloride with amine, followed by using pyridine as a catalyst, the product will be an amide. So all you have to do will be to replace the Cl group of the acid chloride with this part of the amine. So a bond is formed between the carbonyl carbon of the acid chloride and nitrogen of the amine. And that's going to be your product. Normally, HCl will form as a byproduct, but the pyridine will neutralize the HCl. So to predict the product of this reaction, here recognize that though this is a cyclic compound, but it's an ester, so we have a cyclic ester. And whenever you treat ester with diol H, the ester will be converted to an aldehyde. So what diol H does is that it supplies a hydride in limited amount. So essentially what happens is that this hydride will make a bond with this. Eventually, this bond is going to break, and that will form an acyclic compound. So in other words, this is a ring opening reaction. So in step 1, we would open up the ring where the hydride gets attached to the carbonyl carbon. So if I number this as 1, 2, 3, 4, 5, oxygen 6. So this is 1, 2, 3. It's always a good practice to number your carbons so you don't miss your carbon count. So 1, 2, 3, 4, 5, oxygen 6. So that oxygen should have a negative charge. Now in step 2, that oxygen will pick up a proton from the aqueous acid and forms an alcohol. So your product eventually will be this. So in this question, we are told specifically that this reactant is in low concentration and that a product is not a polymer and neither is it an oligomer. So that means we're going to have a ring opening reaction. So essentially, when you subject amide to hydrolysis, you will form carboxylic acid. Now what's going to happen is that the hydroxy group from the sodium hydroxide is going to make a bond with this carbonyl carbon. Eventually, this bond is going to break and the excess electron will go to the nitrogen. Now, it's always a good practice to number your carbons so you don't make mistakes. So if we make this carbon 1, this will be 2, 3, 4, 5. So that bond between the carbonyl group and the nitrogen will break. And the OH group is going to be attached to that carbon 1. Now, carbon 1 is joined to carbon 2, which is joined to carbon 3, which is joined to carbon 4. Carbon 4 has a methyl group, and the carbon 4 is also joined to carbon 5, and carbon 5 is joined to nitrogen with a hydrogen atom. Now, that nitrogen has a negative charge because it accepts electron. Now, in step 2, the nitrogen, negatively charged nitrogen, is going to pull off a proton from the aqueous acid, and it will form an amine. So your product would then be H2N and then you have carboxylic acid on this end. So let's number our carbons to make sure that this is correct. 1, 2, 3, 4, 5. Carbon 5 is joined to the NH, and carbon 4 has a methyl group. Let's remember to include that. Okay. So that's going to be the product of this reaction. Again, in this question, we're told that the concentration of this reactant is low. A product is not a polymer product. Now, it's a good practice to number your carbons. So we have 1, 2, 3, 4, and 5. So this is a ring closing reaction in which the nitrogen is going to make a bond with carbon 1 of the acid chloride, and that will form a 6-membered ring. Of course, in this reaction, HCl is usually formed, which will be neutralized by pyridine. So we're going to have a 6-membered ring. So that's going to be the product of the reaction. Now, specifically, we are told that this is a polymer product, and we're given this reactant to be in high concentration. This is a molecule or a compound that has 2 functional groups, amine and acid chloride. Now, what happens is that the acid chloride group of this monomer unit can react with the amine of another monomer unit. And this amine can react with the acid chloride of another monomer unit. So we know that the nitrogen of this monomer unit can make a bond with this carbonyl carbon, and then the Cl group is going to leave. So I can draw a bond from this nitrogen to the carbonyl carbon. I don't have to draw the carbonyl carbon in the product. I can just place a bracket here and erase one of the hydrogens. That hydrogen will be picked up by the pyridine. Now the acid chloride here, the carbonyl carbon of this acid chloride is going to be attacked by another nitrogen of another monomer unit, and it will make a bond. So this carbonyl carbon will make a bond with the nitrogen of another monomer unit. In the process, the Cl is going to be kicked out. So what I would do is to make a bond between this carbonyl carbon, from this carbonyl carbon. I don't have to draw the order. You can just place an N here, where N represents a positive integer, which could be in hundreds or tens of thousands. So you can draw your product as, your polymer product as this. But this is how to figure out what kind of polymer product you would have. In this reaction, a bifunctional molecule that has two functional groups, alcohol and carboxylic acid, is reacting under acidic conditions to form a cyclic product. So we're told specifically that a product is a cyclic product and not a polymer. So this reaction is a ring closing reaction. And the name of this reaction is Fischer-esterification. That's the reaction that involves carboxylic acid with alcohol under acidic conditions. And in Fischer-esterification, an ester is formed and water is eliminated. A good practice would be to number these atoms. So the oxygen from the alcohol will make a bond with carbon 5. And this is going to form a 5-membered ring. So we'll have an ester that is 5-membered ring. And that will be the product of the reaction. So there are multiple steps in this reaction. We have ethyl bromide reacting with magnesium. The ensuing product is then reacted with carbon dioxide, followed by treatment with aqueous acid. So when you treat the ethyl bromide with magnesium, you will form this Grignard reagent. So you form ethyl magnesium bromide. So this is the product from reaction from step 1. If you treat this with carbon dioxide, carbon 1 of the Grignard is going to attack this carbon, and that will push the pi electron towards the oxygen. So an extra carbon is formed. And in the third step, so this is step 2, in step 3, this negatively charged oxygen will pick up a proton from the aqueous acid and forms OH. So essentially you would have this carboxylic acid as your final product. This is a multi-step synthesis problem. So for this type of problem, you're going to solve it serially. Start with step 1, followed by step 2, 3, and 4. In step 1, when you react aniline with sodium nitrite in HCl, that's going to form a diazonium salt. So you have this arene diazonium salt. When you treat that diazonium salt with copper 1 cyanide, the N2 plus will be replaced with the Cn group. And so you're going to have the nitrile. And when you treat the nitrile, so this is step 2, if you subject the nitrile to hydrolysis under acidic conditions with heat, now the nitrile is going to be converted to carboxylic acid. So you're going to have benzoic acid. Then if you treat benzoic acid with methanol under acidic conditions, that's Fischer esterification, and you're going to form an ester. And the ester will be such that you're going to replace the OH group with this methoxy group from the methanol. That will be your final product. So this section covers mechanism questions. This is Fischer esterification. We're treating benzoic acid with methanol under acidic condition to form our ester. So you're asked to propose the mechanism for this reaction. Since methanol is a weak nucleophile and the reaction is taking place under acidic conditions, the first step of this reaction is going to be protonation. So we're using catalytic HA, which is catalytic acid. So the first step here is going to be protonation. So we protonate the carbonyl group, the carbonyl oxygen. And the conjugate base of the acid is formed. This step will then be followed by the nucleophilic addition, in which the weak nucleophile can now attack this carbonyl carbon, which will push the pi electron towards the oxygen, thereby neutralizing the positive charge on the oxygen. Now a new bond is formed between the carbonyl carbon and the oxygen of the methanol. We're going to give the oxygen a positive charge because now oxygen has 3 bonds. The next step is going to be proton transfer. And what we're trying to do is we want to eliminate OH group, but OH is a bad leaving group, so we need to convert it into an excellent leaving group. And to make that happen, since we don't need the positive charge on this oxygen, so we could use this OH group to grab this proton, and that would neutralize the positive charge on that oxygen. So this becomes OH2 plus, and then we have the methoxy group here. So the next step is going to be elimination of water molecule. To eliminate water, the lone pair on this oxygen could collapse, forms a double bond here, and thereby kick out the water molecule. And in the final step, we will do deprotonation. So we need to get rid of the positive charge on this oxygen. To do that, we could use the conjugate base to remove this proton. This bond is going to break, and the excess electron will go on to neutralize the positive charge on the oxygen. And the catalytic acid is regenerated. So this will be the mechanism for converting the carboxylic acid to the ester. Let's go to the next question. This is transesterification. So here we're converting this ester group to another ester. So we're going from ethyl propanoate to methyl propanoate. Now, the mechanism for this reaction is similar to the one we just did, right? Because this is a mechanism involving the ester with a weak nucleophile under acidic conditions. So as usual, the first step in this mechanism is going to be protonation. So you protonate this carbonyl oxygen. And the conjugate base of the acid is formed here. After protonation, you can now do nucleophilic addition. So the weak nucleophile, methanol, can now attack, the oxygen from the methanol will attack this carbonyl carbon. That will break this pi bond and push the pi electron towards the oxygen to neutralize the positive charge on that oxygen. That would then form an OH group. And this is the new nucleophile. This is the nucleophile that is now attached to the carbonyl carbon. Because oxygen donates electron to the carbonyl carbon, we will give the oxygen a positive charge. Now, since we need to replace, if you look at the equation or the reaction, we are replacing the ethoxy group with methoxy group. So that means we're going to eliminate this ethoxy group and replace it with this OCH3 group. So the next thing to do will be to eliminate this ethoxy group. But to do that, we need to convert that ethoxy group from a bad leaving group to a good or excellent leaving group. To do that, we'll have to do proton transfer. So this oxygen here pulls off this proton, and then this bond between oxygen and hydrogen will break, and the excess electron will go on to this oxygen to neutralize the positive charge on that oxygen. So the next step would then be elimination. To eliminate the ethanol, the lone pair on this oxygen will collapse and forms a double bond here, and that will break this bond, and the excess electron will go onto this oxygen, thereby kicking out the ethanol as the leaving group. So we need to find a way to get rid of the positive charge on this oxygen. And to do that, we'll have to do deprotonation, in which the conjugate base will remove the proton, then the bond between hydrogen and oxygen will break, and the excess electron will go onto the oxygen to neutralize the positive charge on that oxygen. And we'll end up forming our methyl propanoate ester. And of course, the catalytic acid is regenerated at the end of the reaction. Next question. In this reaction, we're converting acetone, which is a ketone, to acetal. Again, we're asked to propose a reasonable mechanism to show how this reaction will take place. Like I said previously, most reactions under acidic conditions follow similar pattern. So the first step here is going to be protonation. The carbonyl oxygen of the acetone will grab this proton from the acid, and we'll have this protonated ketone. After protonation, we will now have our nucleophilic addition. So the oxygen of the methanol would attack this carbonyl carbon, and that will push the pi electron towards the oxygen. So a new bond is formed between the carbonyl carbon and oxygen of the methanol. So we're going to give the oxygen a positive charge, since that oxygen now have 3 bonds. After nucleophilic addition, we would now have proton transfer. This hydroxyl oxygen will pull this proton. Now the next step is going to be elimination. Since this is an excellent leaving group, water will be eliminated and would have OCH3. And since this carbon loses electron to the oxygen of the water molecule that forms, we'll give that carbon a positive charge. This can undergo resonance. Now this is extremely reactive, and so that can react with another molecule of the methanol. So that's why we're using this methanol in excess. So you have another nucleophilic addition. So to get rid of the positive charge on the oxygen, our final step is going to be deprotonation, where the conjugate base that is formed at the initial stage of the reaction would now get rid of this hydrogen or proton. So our final product will be this acetal. And the acid catalyst is regenerated at the end of the reaction. Now in this section, we'll be covering basically synthesis problems. Now in order to solve this synthesis problem, the challenge here is that these substituents are all auto-para directors. However, notice that they are meta from one another. So that poses a challenge. Now, one of the methods we can use to solve this synthesis problem is to use diazonium chemistry, in which case we'll first of all do Friedrich-Krafft alkylation. So attach the isopropyl group at this position. So to then attach these bromo groups, we will need to install a group here, such as NH2. What this NH2 will do is that it will help to direct the bromo groups to the auto positions. And after attaching the bromo groups at the auto positions, we can now go ahead and remove this NH2 group using diazonium chemistry. So this will be the template to solving the synthesis problem. Let's go ahead and write out the synthesis solution to this problem. So like I mentioned previously, we will need to install this first, and that step involves Friedel-Crafts alkylation, in which we will treat this alkyl halide with, we can use aluminum trichloride. So that helps us install the isopropyl group. Next, we can go ahead and install the NH2. And to do that, we'll first of all do nitration. So this will install since the isopropyl group is an auto-para director, so that means we're going to form two possible products. The NO2 could be attached at this auto position. And it could also be attached at the para position. Since we're interested in the para product, so we're going to separate this product from the mixture and continue our synthesis with it. We will convert the para product from NO2 to NH2. And to do that, we could use ion in HCl in order to prevent the NH2 from getting protonated. We can add a small base here after the reaction. Now that we have the NH2 group, we can now go ahead and install our bromo groups. So that means we could do bromination twice. So when you treat that product with bromine in using ion tribromide catalyst, so a bromo group will be attached here. If we repeat this step twice, the second bromo group will be attached here. Now we have to go ahead and remove the NH2 group. And to do that, we will need to treat the aniline with sodium nitrite in HCl. That will convert the aniline to diazonium salt. To then remove the diazonium salt, we will need to treat it with hypophosphorus acid. And that acid usually will remove the N2+. To solve this synthesis problem, we need to recognize that a product is an ether. And to make ether, you will need to react a strong nucleophile with an alkyl halide, usually primary alkyl halide or methyl halide. So that means I need to break this bond here in order to determine the fragment or reactant I need to use. So if you break that bond, you would have a strong nucleophile reacting with CH3. You just make this into CH3Br, so methyl bromide. So this gives me an idea on how to plan my synthesis. Okay, so let's apply retrosynthetic analysis, working backwards. So I'll be reacting the alkoxide with methyl bromide in order to make the ether. And this goes through an SN2 reaction. So we can work backwards from here and later on work forward and then eventually complete the synthesis. Now the question then becomes, how can we make the alkoxide? We can make this alkoxide by deprotonating alcohol. So if you deprotonate this phenol using sodium, metal, or even sodium hydride, that will deprotonate the alcohol. Now, how can we make an alcohol? How can we add the OH group to the benzene ring? To do this, we could use diazinon chemistry, in which if you treat this arene diazinon salt with aqueous acid, that will convert the N2 plus on the benzene ring to OH group. How can we make diazinon salt? We can make diazinon salt by reacting aniline with sodium nitrite in HCl. And to make aniline, normally we would reduce nitrobenzene. We will reduce nitrobenzene using iron in HCl. And of course, we could always do another step where we add sodium hydroxide to prevent protonation of the aniline that is formed. Now, to make nitrobenzene from a starting material, benzene, we will need to do EAS nitration reaction, in which we will treat the benzene with nitric acid and sulfuric acid. So this is working backwards. We could also work forward from here. So now that we've made the ether, the next thing would then be to attach the two Cl groups. But recall that methoxy group is an autopara director. In order to optimize our product yield, the ideal thing to do would be to block this para position first with a reagent that can easily be removed thereafter. So after blocking the para position, we can now go ahead and add the chloro groups at the auto position. So the next thing we want to do now is to block the para position. To do that, we could also use the diazinon chemistry, in which we can react this with, we can do nitration, HNO3 and H2SO4. That will give us two products, auto and para product. So NO2 will be attached at the auto product, and we will also have the para product. Now that we've blocked the para position, we can go ahead and do and attach the chloro groups at the auto positions. So we can do Cl2 and AlCl3. That will add Cl group here. If we repeat this process twice, the second chloro group will be attached here. Now we can now go ahead and remove the NO2 group. To do that, we could use diazinon chemistry, in which we will convert the nitro group to NH2, then treat the NH2 with sodium nitrite in HCl to convert it to diazinon salt, and then treat that diazinon salt with hypophosphorus acid to remove the diazinon, the N2 plus. So next thing will be to reduce the NO2 using iron in HCl. Of course, we can always do a second step involving sodium hydroxide to prevent protonation of the NH2 group that is formed. We can now treat this compound with sodium nitrite in HCl, and that will convert the NH2 to N2+. So we'll form a diazinon salt. We can now go ahead and treat this diazinon salt with hypophosphorus acid, and that will remove the N2+, thereby giving us our final product. This reaction asks us to propose a reasonable synthesis that could transform this primary alcohol to this tertiary amine. So the ideal thing to do here is to try to determine what reagents or reactants we will need to use in order to make this amine. So I could cleave this bond here, and I could also break this bond here. So this will give us so I have this fragment, then I have this fragment, and I have this fragment here. So this gives me an idea of what reagents to use for this synthesis. Now I'll have to then convert these fragments into meaningful reagents. Since this one looks like our starting material, I can make this into an alcohol. Then I can make this one into amine. Now, another question I will have to ask myself is, how can you make an amine? There are different methods you could use to make an amine, but one of them is the reduction of amine. Reduction of amine. So, and to make an amine, you will need to react a carbonyl compound, such as aldehyde or ketone, with a lower degree amine. In terms of the product, all you have to do is to replace the carbonyl oxygen of the ketone or aldehyde with nitrogen of the amine, and the R group on the nitrogen remains the same. The byproduct in this reaction is water, the carbonyl oxygen and the hydrogen from the amine. Now, when you reduce this, you can now form the amine of choice. So that means from a starting material, I will need to make this into a carbonyl compound. Preferably, this would be an aldehyde. This is going to be an amine. This is going to be an aldehyde. So I have to make this fragment into an aldehyde. And that's because the carbonyl compound of choice must have just 2 carbons. So that's why that has to be an aldehyde. Now that I have the fragments I'll need to use for the synthesis, I can then go ahead and plan my synthesis. So for the synthesis problem, the first step is going to be to find a way to convert the primary alcohol to this aldehyde. To do that, the reagents of choice is usually PCC. We could do this in methylene chloride. Now, the next thing to do would be to react this aldehyde with this primary amine. in order to make an amine. We can then reduce the amine. So I'll treat this with this primary amine. So when you react the aldehyde with this ethylamine, we'll do this reaction under acidic conditions. So that's going to make an amine. And the amine is going to be, start by drawing your carbonyl compound, aldehyde, then replace that oxygen of the aldehyde, replace this oxygen with the nitrogen of the amine. And the alkyl group, the ethyl group, remain the same. Now the water is usually a byproduct, and the water comes from the carbonyl, oxygen, and the hydrogen of the amine. So this is going to be the amine of choice. Then you can reduce this amine using sodium borohydride. So that will form the secondary amine. So now we've successfully we've made this part of our starting material, of our product. The next thing would then be to attach the ethyl group to the secondary amine. To do that, we will have to then react this secondary amine with the next reagent here, which is the aldehyde. So we're going to react the secondary amine with acetaldehyde. And when we do that, the product will be, so we'll do this reaction under acidic condition. Again, to draw the product, the amine, start by drawing your aldehyde, replace the carbonyl oxygen of the aldehyde with the nitrogen of the secondary amine. In this case, we'll form an iminium ion. This is quite unstable. So to reduce this iminium ion to a final product, which is a tertiary amine, we're going to use a modified version of the sodium borohydride. More specifically, we will use sodium triacetoxyborohydride. Sodium triacetoxyborohydride. The solvent is usually acetic acid. We could also use sodium cyanoborohydride. However, that's usually kind of toxic. So the most preferable reagent to use in this case would be this. So when we do this reaction, the iminium ion is going to be reduced to the tertiary amine, and that will be the synthesis. All right, good luck with your exam. I'll stop here today.